recap of my winter break. Oh, here it is. Just sort of what I did over the break. We traveled a lot over the break. We went to Colorado. We have family in Colorado, in Fort Collins, and Denver, near Denver, Arvada. So we spent a week, more than a week there. Went skiing a day, sort of played in the snow a lot. We got a lot of snow. It was good weather playing in the snow. Let's see, this is us skiing. We went to Loveland Ski Resort, made cookies with their grandmother, my wife's stepmom, and then hung out with cousins in Arvada. We went to Mississippi. This is us. We were geocaching in Mississippi. That's me and our kids. Saw my dad for a while. And then this is a cell phone tower on the right. But this cell phone tower is named after my brother. Isn't that cool? Like, he manages cell phone towers. He does heating and AC stuff, so he sort of maintains their facilities. And after like 10 years of service, they named a cell phone tower after it. It covers like T-Mobile, AT&T, a whole bunch of carriers. If you go through Pachuta, Mississippi, you're probably going to use the cell phone tower, the Joey Young cell phone tower. And then we stayed in Louisiana, of course, for a while. My wife and I, we went out to Jean Lafitte Preserve. You ever been out there? Out near New Orleans. Yeah, pretty cool place. We've never been before. We saw some alligators. Saw a bunch of alligators actually. Even though it was kind of a chilly day, they were still out for the sun. We went to a conference. I think I might have sent you all this picture. Did I send you this picture? My wife and I went to this physics education conference in New Orleans. The AAPT. I have a poster up actually. If you want to take a look, we did the physics of weightlifting. But this guy gave a talk. Y'all know who this guy is? Yes, you do. You know who that guy is, right? Who is he? Derek Muller. Does that ring a bell? The Veritasium guy? I found his videos in class for a really great YouTube channel. And my wife and I, we really liked him. We sit right up on the front row, and it's like he was talking to some people in the front row, and then he comes over to us, and we were just sort of starstruck. My wife, we didn't really know what to say. My wife says, "We're really big fans of yours." And then I said, "We've never met anybody famous for. We don't really know what to say." So, but he was really cool, and he's a lot cooler than I am. He's a really good educator, and just a really neat guy. He's also Australian, which you can't really tell now. He sort of changed his accent. But we got a selfie with him, like any self-respecting fan would do. Had Christmas time, had some cool gifts. My son gave my wife a gift for a free haircut. Not that she would get a free haircut, but that he would allow her to cut his hair. Because he hates haircuts. And she doesn't like it, the hair being all down on his neck and stuff. So gave him a free haircut. Some of y'all, she could do some work on you too. Right? But so anyway, that's him getting a free haircut. And then they got their rooms painted for Christmas. Or rather, my little daughter got her bed painted for Christmas. She has a loft bed. So she got it painted pink with big white polka dots. And she has a sky underneath with her sun and clouds. And my son got his room painted just like really dark blue. That's what he wanted. So that's what we spent several days doing, painting rooms for Christmas gifts. I think that's it. I also like to, on the second semester, do an interview time. We did this last semester, you remember? The first day of last year, where we have a few minutes for interview time. This is where you guys get to ask questions of me. So you've known me for like a semester, most of you. But we'll take about 4 minutes or so. Where's the sun coming from?
Right there.
I can't do anything like that little crack, and so you can move your desk and we'll put it
It's come from through the blind thing itself.
Oh, I'm sorry. Y'all can move it if you want.
She said from the blind.
Yeah, just
I just can't see it at the moment.
Let's see, interview time. So we'll spend 3 or 4 minutes. Y'all can just ask me whatever questions you want. Like, we're just gonna sit here for 3 or 4 minutes and just be silent and we don't ask any questions. Yeah.
Where'd you go to college?
What's your name again?
Tucker.
Tucker, right. So I went to UT Austin, and for graduate work in astronomy, I'm an astronomer. I think most of it, but at Mississippi State, part of it. Logan?
How much do you like astronomy?
How much do I like astronomy? I like it a lot. Oh yeah? You might want to start like with a pair of binoculars, I think. You might even have a pair of binoculars. Like low-end telescopes are kind of difficult to use. I think sometimes people get frustrated with it. But to start, you should go to your Facebook, a Facebook account. You could go on there and search for, what is it? Nichols Astro, but of course it's spelled E-A-U-X. And they just sign up, it's a group, like it or whatever. I don't know how to do that, you like it, I guess. And it'll tell you about star parties. There should be a star party coming too. And then you can sort of get a feel for what telescopes we have. Alright. Yeah, what? My favorite topic in this class? I like the circuits a lot. They're sort of like Sudoku puzzles, right? Just sort of getting a feel for the puzzle, the circuit as it may be. I like that. And it's not that complicated really. It's just sort of seeing things spatially and dealing with simple numbers. There's a lot of fun. I feel like you might be interested in that. All right, do a couple more. Okay. This isn't much fun in the second semester, is it? What does it?
It's good right now.
Right, yeah.
How's your Greek coming along?
Oh man, that class kicked my butt. It was a tough class, but I finished it. I made an A. Actually, I came up to the final, and I figured out I needed like a 30% to still get an A. I hate when y'all do that, like when you figure out what you need on the final to get an A in the class. But I found myself doing it too, like, oh goodness, what do I need to get? And so I needed a 30%. So I wrote my professor ahead of time and said, look, I only need a 30%. I'm probably not going to do very well on this final, okay? I just want to prepare you for it. She said, oh, that's fine, whatever. But then I did really well on the final. I made like a 98%. Yeah. All right. Logan? We do a lot of circuits. Yeah. In fact, like where we used to do light in this course, we've taken out light and we put in AC circuits. So we get into LC circuits, LRC circuits, oscillating circuits. We do all sorts. It's fun. You'll like it. Yeah.
What class did you say you made an A?
I just finished my second semester of Greek. I'm in seminary. I'm working on a master's divinity. So I took intermediate biblical Greek. Made an A. This is the toughest class. In my taking a lot of classes.
Are you taking it this month?
Taking preaching. It's a practical course. It's a joy. All right, folks. Any other questions? No? All right. I'm not going to spend a whole lot of time on the syllabus. Just want to sort of point out a few things. I've sent out the website, but it is on Moodle, so your Moodle page should look something like this. As you know, I'll use this to post your grades and stuff, but you can get access to the website through here. Just here. A few things. Let's look at the syllabus. It's a lot the same as last year, or last semester. So I'll just sort of point out a few things. Though if you're new to the course, you might want to, if you want to come by for a few minutes after class, I can just give you the 2-minute version of the syllabus and point out certain things. But let's see, a lot of the same. Loosely follow the Halliday, Resnick, and Walker book. If you want to buy that, that's fine. But I don't require a textbook. But if you want to use it, that's fine. Any version. The older versions are really cheap, so you can buy one of those if you like. This is our test schedule. Light gray are our exams. We have 4 exams. These are our exam dates again. There is homework. It's on the website. It's in your workbook. You will use your clickers this semester. Those clickers, you get a maximum of 50 points. As I said last semester, the way you get a certain amount of credit if you get the answer wrong, twice that credit if you get the answer right. The way I figure out that credit at the end of the semester is I say, okay, I have X number of questions. And right now, I don't know exactly how many questions we'll have. But I say if we have X questions, if a student got they answered all those questions and got half of them right, then they get the full 50 points. That usually means that everybody that comes to class regularly maxes out that 50 points somewhere between the 3rd and 4th exam. Because there's a lot of sort of extra points built in. But if you miss a lot of class, if you're missing a 3rd of the classes, I wouldn't expect to max out that credit. But just do the best you can on those questions. Those will be multiple choice questions I will pose during class. you answer with your clickers. This is how we assign the grading. This is the same as last semester. Makeup's the same. If you make up, if it's excused, just contact me as soon as possible, even the day before the exam if possible, or the week before, depending on how long you know that you know. But if it's unexcused absences, I deduct 15 points from your exam grade right away, and then 3 points for every subsequent weekday until you contact me. There's drop day. This grade calculator is a spreadsheet. You can use that to calculate your grade. If you want to do honors credit, I think honors credit is due in February soon. It's in a few weeks. So if you want to do honors credit in this class, you can look here for some ideas. You will have an equation sheet for this class from the very beginning. Just be familiar with this. This might be in your workbook. I'm pretty sure. I don't remember if I put it in there, but you'll want to just print it out just to be familiar with what's on that equation sheet, because you'll have this for all the exams. You can find old exams here. Go to Physics 202. New folks, you'll probably use this, the old exams, and then there are also solutions to all the exams. They're just videos of me working through those exams. So for example, this is exam 1 from a couple years ago. And I just go through and work through all the problems. So I'll do that for your exams as well. Screencast here, I record all the classes, so I'll just dump them here on this website. If you miss class or whatever, you can catch up with what you missed there. Or if you just didn't get something, you can catch up with it there. Help sessions and stuff I'll put there as well. And then some textbooks. Halliday and Resnick is sort of the go-to for calculus-based physics. So if you want to do this, this one looks like it's about $35, but if you get an older version, you can get it even less than that. Most of you aren't textbook people, and I understand that, but if you want a textbook, that's the one to get. All right, any questions about that, Joe? About the course, how it's going to work out? It'll be a lot the same as last semester, those of you that had last semester. The homework? Okay, yeah, the homework. You know, let me explain the exams first. Okay, the exams are about 15 to 20 multiple choice questions. That'll be sort of based loosely on the clicker questions that we have in class. And then you also have free response questions. You'll have 4 to 6 free response questions. To practice for those, you want to do the homework. And the homework is in your workbook. It's also on the website, and there are solutions to all the homework, video solutions, and me working through the homework. So sometimes you might just see a homework question straight up on the test, just with different numbers or slightly changes, or problems that are similar to the homework. You can also look back at the old exams for ideas about what might be, what to expect on this. All right, I don't take up the homework, I don't grade it, but it's there for your practice. Did I explain enough for you? Yes. Any other questions or things I might have left out? No, right now? All right. Listen, my office hours are on that website. My office is just down the hall. I have office hours from 7 to 7:30, which is usually set aside for you guys because, you know, nobody else here really at 7 o'clock, but sometimes y'all do get here early. But I have other office hours as well. I don't have class right after this class, so that's a good time if you want to catch me. I think that might actually be part of my office hours. Yeah, so I have office hours right after this class. That's a good time, maybe, unless you have class. But listen, if I'm not in class, which, you know, is a lot of the day, then I'm available to you. So if you need help and I'm not in class, then please just drop by. If you want to make sure that I'll be in my office when it's not my office hours, then shoot me an email or give me a call or whatever. All right? I'm here to help you do well in this class, so don't forget that. That's my job, is to help you do well. All right? Questions? No? Okay. Well, let's start with chapter 0. And again, I'm sort of calling this chapter 0 because it's really just a precursor trying to introduce fields. Because when we get into electric forces, we'll find that electric forces and fields act basically the same as gravitational forces and fields. So the stuff that we're seeing now in this chapter, this sort of small chapter, we'll see in even greater detail in a couple of chapters when we get to electric fields. Electric fields and gravitational fields are very, very similar. It's just, you know, the nature of the force or the way the force is caused is different. But they act in the same way. You'll also see some stuff that we've already done, like just vector addition. We're going to do that for the next few chapters, adding up vectors in 2 dimensions, just to make sure that we've got that down. And then we'll also see some new things with flux and integrals and what have you. All right, so first of all, Newton's universal law of gravitation. Isaac Newton, he was 23 when he first showed that a force causes the moon to be attracted to the Earth, and that's what caused them to orbit about one another. And that's the same force that causes something to fall, right? This is sort of the what's the word? The legendary story that the apple fell and he figured out that it was because of the gravitational force. We don't really know that happened. But he described this force in this way, that F is equal to big G, this is a gravitational constant, times the mass of the first object times the mass of the second object over r squared. I'll call this M1 and M2. Usually when we write a capital M and a lowercase m, the capital M means the mass of the Earth, and the lowercase m means the mass of the object. But that's not terribly important. So if I have 2 objects of mass, I have M1 here, I have M2 here. They're separated by a distance r. The force between them is given by that. This is actually the magnitude of the force. We know that objects of mass are attracted to one another, so these forces then are going to be in this direction. So I have the force on particle 1 due to particle 2, and then I also have the force on particle 2 due to particle 1. These forces are equal and opposite, and they're both given, and both of their magnitudes are given by this expression. So Isaac Newton figured this out, or he described the forces in this way. Just a few things to note. I've already said some of this, but F is the same for both. For both masses. F is proportional to the mass. That is, you know, F is proportional to M. It's directly proportional. If I increase one of the masses by a certain amount, by a certain factor, I increase the force by that same factor. F is inversely proportional to R, actually R squared. This is an inverse square law, we call this. And the fourth thing, this law applies to particles. When I say particles, I mean point masses, that it applies to point masses. And, oh, but you say the Earth and the Moon, those aren't point masses, right? But they're significantly far away from one another, and then we'll also see that Newton described something else, which makes that whole point sort of moot. Newton proved the Shell Theorem, and the Shell Theorem, in his creation of this universal law of gravitation, he proved the Shell Theorem, and it says that a uniform spherical shell of matter, like the Earth, for example, which is fairly uniform, fairly spherical, a uniform spherical shell, so not like the Earth, I'm sorry, but like a shell, like a ring, like a ball that's empty in the middle. A uniform spherical shell of matter attracts a particle that is outside the shell, as if the shell's mass were concentrated at its center. So he basically said, let's say that I have a ball of matter that's empty in the middle, and then I have another object over here this other object's going to feel a force that's exactly the same as if that ball of matter was all condensed down to one point. Draw a picture for that. So I have a ball here that's empty in the middle, I have a point mass, these experience a certain force. That's exactly the same as if I had 2 point masses that were the same mass, that they would feel the same force. It doesn't matter that it's a shell, it looks exactly the same from the outside. Now if you're inside the shell, it's a little bit different. He also had something to describe that as well. We're not going to get into that. We're not going to do the derivation for this, so I do want to show it to you. Some of you have seen, and actually you could probably go through the derivation, it's not that complicated. But he showed this by integrating a shell. Or integrating over a shell, and showing that the universal law of gravitation was correct. That is that F equals G mm over r squared. Oh, by the way, I didn't give you the value for G. It's on your equation sheet. G has a value of, what is it? I think it's 6.67. It's 10 to the minus 11. Let me verify that right quick.
Yeah, it's -11.
Okay. And let's see, the units for that are Newton meters squared per kilogram. You don't need to know that number, of course. Newton meters squared per kilogram squared, right? Okay? But that's on your equation sheet. So he integrated a shell, and then he showed that F is equal to G mm over r squared. Again, you're not responsible for showing how he did this, but let me just show it to you. We'll just step through it in just a couple minutes. I think the wiki page has a pretty good thing on the Shell theorem. Yeah, here we go. All right, so basically, Newton took a shell of matter. This is a ball that's empty in the middle. It's just a thin shell of matter. And he took another point mass that's over here, and he asked the question of, what is the force on this point mass due to this distribution of mass? Now, in order to do this, he would split the shell up into differential elements, right? He split these up into differential elements and asked, okay, what is the actual force on this point mass due to this differential element? And then he integrated over that differential element. Follow the general idea? We've done that before. We did that last semester. So the first thing he did was to define what is that force on that differential element right here. Let me zoom in a little bit. So this is the force on that mass element. We have a differential mass element. Remember, we break it into little bitty pieces of n. And then we find the force, dF, on that particular piece. And then we add up the forces for all those particular differential elements. That's what we do when we integrate. Made some assumptions here because the forces are all in one direction, so he just takes the x component. That's where this cosine of phi comes in. This is integrating over the forces, and has some various substitutions here using the law of cosines, which we're not going to get into. But you should have seen that in your calculus class, or you will see it this semester. Are all of y'all in Calc 2 this semester? No, I guess some of you biology folks are not. Is that correct? Don't worry, it's not going to be too bad. And so then you integrate over the shell. This is just sort of showing that adding up the force going around the shell, that's what an integral does, is to add up that force. And then he showed that, through some various substitutions here, that the total force, when I add up all those forces, is equal to this G mm over r squared. So the force on a point mass m is equal to G mm over r squared if it's a shell or if it's another point mass. That was the point. The Shell theorem just says that a shell on the outside looks like a point mass. All right? If you don't get anything from this, that's not a big deal. But you do need to know what the Shell theorem is. You could have, those of you that are new, sometimes I will put some short answer things on your test that might be worth 5 to 7 points or so. So for example, I might say, describe to me the Shell theorem. And you have to answer in a few sentences, what is the Shell theorem? It doesn't have to be exactly what's written here, but something similar. You could draw a picture, write an equation, write a couple sentences, whatever. So let me, so if we think of the Earth, this is the Earth, we can think of the Earth then as a bunch of little shells. So the Earth consists of a bunch of shells. Sorry, I don't have my colors. Figure that out. So we can think of the Earth as a bunch of different shells, and if we have a point mass m over here, we can figure out what is the force due to, say, the blue shell, what is the force due to, say, the black shell, and then what is the force due to the red shell, and we can find the total force by adding up each of those individual forces, and that's what Newton did. So in short, this is the superposition principle. We saw this last semester, where if I have a bunch of different forces and I want to find the total force, I just add them up. We can do this through integration, and we'll do this in the next chapter when we figure out the electric field and electric forces on a charged object. But we can also just do it through vector sums, which we've done before, and y'all should be okay on, but you'll see it again on this first test. You're probably not going to see it past the first test again, but just sort of one last grab at making sure you can add up vectors. So the superposition principle says with, sorry, I don't know what it says here. I forgot, I printed out the wrong thing. But with multiple masses, one can find the total force by calculating the vector sum of the individual forces, just by adding up all the forces. So for example, let's say that I have these three masses, and I want to know what is the net force on M1. So the way I like to do this is first draw all the vectors that are acting on M1. How many vectors are acting on the mass M1? 1, 2, 3, 4. How many? There are two vectors. I have a vector on M1 due to M2. What is going to be the direction of that vector? Down, up, left, down? What do y'all think? Now remember, gravitational forces, are they attractive or repulsive? They're attractive. So the force on M1 due to M2 is going to be in which direction? It's going to be up. Right, so the force on M1 due to M2 is going to be up. So this force, I'll call this F12, and that's the force on particle 1 due to particle 2. And then the force on particle 1 due to particle 3, what's going to be the direction of that? To the left, right. So I have this force to the left. F13. My next step is to find the magnitude of each of these forces. I know from Newton's universal law of gravitation it's G mm over r squared. So I can find F12, the magnitude of that force is going to be 6.67 times 10 to the minus 11. Times M1, which is 6 kilograms, times M2, which is 4 kilograms, divided by r squared. A is 2 centimeters. You'll need to convert that into meters, 0.02 meters squared. And that gives me a magnitude of that force, F12, 4 micronewtons. 4 times 10 to the minus 6 newtons. So not a big force, but it's measurable. In fact, you can, with a simple device, you can measure that force. All right, then we can do the same for F13. It'll take just a minute. Find the magnitude of F13. And then I want you to find the magnitude and direction of the resultant force. So remember, that's where you're going to have to use the Pythagorean theorem in order to find the sum of those two forces. This one's pretty easy because they're both either on the x or y axis. And then you'll need to use your tan function to find the angle for that force. So go ahead and find F13, and then find the direction for the sum of those two forces, which I'll go ahead and draw here. Some of those two forces will fall somewhere like this, and you'll want to find out what is this angle. Notice that M1 and M3 are twice as far apart. It's 2a, so this isn't 2 centimeters, it's 4 centimeters, which is 0.04 meters. You could see a question like this on the test. I know that y'all know how to do it, but just to sort of see what you can. I want to point out that these two particles are twice as far apart, these two particles, but have the same masses otherwise. So you would expect this force between these particles, which are 2 times as far away, to be what factor of the other force? 1/4, right? Because it's an inverse square. So if I double r, I quarter the force, which is what we found here. That F13 is 1 micronewton. You might have the magnitude of F1, the vector sum of those two forces. Anybody? 0.002? That's not what I got. No, that should get me right.
4.12 times 10 to the negative 6.
Yeah, that sounds right. So thank you, Venus. I appreciate it. All right, so it's 4 times 10 to the minus 6 squared plus 1 times 10 to the minus 6 newtons. That's the magnitude of the force, but then you also need to know what is the angle theta. Notice I have a triangle up here. There's F13, there's F12, and I want to know the angle of this part, this vertex of the triangle. So theta is the inverse tan of F13 over F12. That's going to be F12 over F13, opposite over adjacent, right? And that works out to be, what did I get for that? What is it? Okay, 26.5 degrees. That's correct. I had a different number. I made a mistake. Is that right? Is that what you got? Anybody? Anybody concur? Is the inverse tan of 0.25? I get 14. 14?
Well, if it's F12 over F13, the inverse tan of 4.
Oh yeah, the inverse tan of 4. It's 76. That doesn't make sense, though, does it? Inverse tan of 1/2. What? Oh, you're looking at the distance. Yeah, we're looking at the force and stuff. Oh, good call. Right, let's see. So it's the inverse tan of F12, which is 4. Oh, my picture's just drawn wrong. Yeah, my picture's drawn wrong. Yeah, so it's 76 degrees. All right. Let me show you why that was a little confusing, because my picture is drawn wrong. The red vector is actually the small vector, and the blue vector is the big vector. So my triangle actually looks like this. All right. We'll see maybe one more vector problem. There's one in the homework. You could see it on the test, but you will see some vector stuff. We have to add vectors. If you're okay with vectors, adding them. We did it a lot last semester. I don't want to take too much time on it. Yeah. Okay, let's look at gravitation near the Earth's surface. We know a couple things from Newton's laws. We now know from the universal law of gravitation that F is equal to G mm over r squared, where again, big M, I'm letting this to be the mass of the Earth. And little n is like whatever's on the Earth. All right. I also know from Newton's second law that F is equal to ma. And so if I put these two together, since these are both gravitational forces, I can equate them and say that G mm over r squared is equal to m times a. And then I can solve this for a, which is just going to be G times big M over r squared. So my acceleration due to gravity is dependent upon the mass, the big thing, the planet or whatever, divided by the radius of that. In the past, we've assumed for G and AG, I'm going to call this AG now. This is the acceleration due to gravity. Or the acceleration of an object due to gravity. And in contrast, G is the free fall acceleration. And we've always assumed these to be identical. That is, the acceleration that an object feels in practice is identical to this. But this doesn't always hold true for a few reasons. So a few reasons why our acceleration of an object is not always exactly equal to what we would expect it to be from this simple derivation. And so there are three reasons why we don't have this. One is the Earth's mass is not uniformly distributed. We talked about this last semester, or I guess I didn't have a lot of you for lab, but my wife, she might have talked to you about this or not. When we did the pendulum lab, remember that lab where we did the pendulum to measure the acceleration due to gravity? In my class, we talked about how there's a mission, or there are lots of missions to measure the acceleration due to gravity, and they just use that pendulum. They have a similar pendulum, it's a little more complicated, but not much more. They go around the Earth, and they have this pendulum that's always going. They measure its period, and they use that to calculate the acceleration due to gravity. A lot of intelligent and as it's going around the Earth, the reason I want to do this is that the acceleration due to gravity changes as you go over different parts of the Earth. So like, for example, if you go over Mount Everest, where you have more mass sort of underneath the pendulum, you're going to experience a larger acceleration due to gravity, just because you have more mass. Or if you go over, say, a big trench in the ocean, you might have lesser acceleration due to gravity. This is useful, right, because you can look for things that are anomalies, that are mass anomalies that you couldn't see otherwise, such as, I don't know, like an oil deposit or a water table or something along those lines, or mineral deposits. So the acceleration due to gravity is different in different parts of the Earth because of the way that the mass is distributed. And we can use that, as I said, to look for things that are anomalous. So the Earth's mass is not uniformly distributed. The Earth is not a sphere. We often approximate it as a sphere, but it's not exactly a sphere. So the Shell theorem doesn't apply. Remember the Shell theorem. If you could explain the Shell theorem in 1 minute, think about right now in your head how you would describe it to somebody that's never heard of the Shell theorem. How would you describe the Shell theorem to someone? You don't need to look back, just think about it. Or if I asked you on the test, how would you describe it? Okay, so remember the Shell theorem is that an object that is a shell will look the same, will experience the same force, or excuse me, a point mass next to a shell will feel the same force as if that shell was collapsed all down to a particular point. Right, so the Shell theorem for the Earth doesn't quite apply, but we apply it anyway because it's not quite a sphere, but it's almost a sphere. And then also the Earth is rotating. So the centripetal force is significant. All right, so let's say, for example, I have the Earth right here, the radius is r, I have an object, say a box or whatever, that's on the Earth, and it's moving around right here. It's at the equator, so this is the North Pole, and the equator is right here. I'm looking down at the top of the Earth, and I have an object that's at the equator, so it's rotating around at the rotation rate of the Earth, as the Earth rotates around. Now, if I were to draw the forces that are acting on this, what are the forces that are acting on this box? It's sitting at the equator, I don't know, in Africa or wherever. It's sitting at the equator, and the Earth is rotating. What are the forces that are acting on that box as it just sits somewhere in Africa? Okay, I have the normal force. What else? I have the force weight as well. So I'll call this MAG. And then I have an acceleration that's acting on this. What is the acceleration? It's sitting on the Earth's surface. What is the acceleration? What type of acceleration do I have acting on this object? The what? No, not it's just sitting somewhere. So imagine that I'm the box. I'm sitting here. I have an acceleration too, by the way, right now. Maybe not quite as much as this box, but I have what acceleration? Negative. What's that? Negative? No, it's close, but they don't usually call it that. What do you think, huh? No, No, not constant. What three?
The centripetal acceleration is the first one.
Right, the centripetal acceleration. Remember, an acceleration changes the force. An acceleration can change a force's magnitude or change its direction. And remember, the centripetal force was this funky force that we saw last semester. It doesn't change an object's magnitude of acceleration, but it changes the direction. So right now, my direction that I'm moving is changing constantly. I'm moving around in a circle on the surface of the Earth at a constant rate, no doubt, but my direction is still changing. So I have this centripetal force that's acting upon me, and so I have the centripetal acceleration. So the acceleration, that centripetal acceleration, is acting in this direction. I'll call that AR. So I can apply then Newton's second law, adding up the forces and setting it equal to ma, just like we did last semester. So that's going to be Fn minus mag. And this is equal to m times omega squared r. Actually, negative omega squared r. This is the centripetal acceleration. Remember, we had AR was v squared over r, but then we can substitute v equal omega r, and we'll get this expression, omega squared r. Y'all remember what omega is? What is omega? Throwing a lot of shell here from last semester. What is it, Roger? It's the angular velocity, right. So remember we had that theta omega alpha. All right, so that's our angular velocity. All right, so I'm going to assume that my normal force is equal to my weight. So that's going to be mg minus mag is equal to m negative omega squared r. I can cancel out all my masses. Boom, boom, boom. And I can solve this for g. So g is equal to ag minus omega squared, subscripts, omega squared r. So here we see that we have this extra term that's added in that changes our g, which we use to find our weight, right, that mg term, that it's not the same now as ag, which is our acceleration, our gravitational acceleration. All right. Turns out that g is equal to about plus 9.83 minus 0.034. That's when you account for the Earth's rotation. And so this comes out to be about 9.8. So it's not much different because of the Earth's rotation, but it is not insignificant too. All right. Can I go down? Yeah, Ainsley?
In this class, it's still like just for ease of calculations using g is equal to negative.
Yeah. Yeah. In fact, you probably won't see this fit. I don't think you might see it. I'll let you know. But, all right. Okay, so we've already seen this for a particle and for the Earth. That's for the like last semester, we talked about gravitational potential energy and how an object on the Earth can have gravitational potential energy with respect to its position in the Earth, with respect to the Earth. But we can generalize this more generally for two particles of mass. First, the reference point where r equals infinity, or where u equals 0. That is, if I have two objects of mass, I want to know where they'll have no energy. Now, potential energy is the potential for motion. So if I have objects that are really close together, they're going to have a lot of potential for motion because they'll be attracted to one another, and if I let them go, they'll move together. Because remember, mass forces, or gravitational forces, are attractive forces. But if I move them really, really far apart, those forces basically go away. So my gravitational force goes to 0 when the distance is very, very large. So when they're an infinite distance apart. All right, let me just sort of draw a little diagram to show you that. So when objects are close, they have big forces, but if objects are an infinite distance away, the forces are equal to 0 because of that g/mm over r squared. If I let r go to infinity, then the force goes to 0. All right, I think that we'll stop there. We have a little bit more. We'll probably wrap up this chapter on Friday. I'll have my clicker questions. I forgot to put them today. But I'll also give you more clickers. If you don't have them, just put them on Friday. All right, folks? I'll hang in there. We'll have a good semester, okay? Yeah. Oh, yeah. Let me just